Good afternoon, honorable guests. I am representative of Shatin College. Our team number is 140062, and our topic is pass through the surface. How we come up with this topic is that once we undo a button, we find that the size of the button is originally larger than the hole. And then we find that how we can undo the button is that we transform the circular hole into an ellipse so that we can pass through the button. And then we base on this concept and come up with this topic. And firstly, we investigate with the passing through object has a negligible thickness, and then the hole can be transformed freely with the fixed perimeter. And here's the general equation for the diameter of the coin that will have a perimeter over 2 of the hole. And here are different shapes of the hole. And generally, the largest regular object that can pass through the hole has the smallest cross-section with the length equal to half of the perimeter of the hole. And next, we want to be more realistic that the object has a thickness t, where t is larger than 0. And here's the general equation for the coin that it will have a thickness t, and the largest diameter of the coin will be p minus 2t over 2. And generally, the largest regular object that can pass through the hole has the smallest cross-section with perimeter equal to perimeter of the hole. And thirdly, we assume the hole is circular in shape and can only be bent at 2 opposite sides, so that the circular hole transforms into an ellipse like this. And here's some background of the ellipse, and this is the standard equation for the ellipse, and this is the information of the ellipse, and P is the perimeter of the ellipse, which is 4AEE, and E is the complete elliptic integral of the second kind, which is this equation. And we consider the cases that the object we are going to pass through is rectangular in shape, and it has a length of 2h and width of 2w. And we put it into a Cartesian coordinate that's shown in the figure. And so that one edge of its coordinate is h and w. And we'll put it back into the ellipse equation and to see whether is there any relation between the maximum area of the rectangle and the ellipse perimeter. And we do the calculation based on these constraints. And these constraints we missed out in our final paper. However, we actually based on these constraints. And we come up with an equation that link up the h and p and w and the e. And however, we find that it is difficult to eliminate the elliptic integral as it doesn't have any algebraic expression. Therefore, we use some numerical method to see if there is any relation between the value of E and the maximum area. And before we submit the final paper, we don't have any result. But we didn't stop. And we even generate more table and even more detailed data. And we find some interesting property that it will reach maximum area when the E has a range of 0.54 and 0.55. And then we find out that when W is equal to B over square root 2, and we put it back into the ellipse equation that we have, we can successfully come up with an equation that can link up with the maximum area and the perimeter. And based on the concept of passing through the surface, we come up with 3 interesting applications. Firstly is the switch. And the switch is based on 2 concepts. Firstly is the Gauss law, which states that the electric field is equal to the charge density and cos over permeability, and also the curvature, which is redefined by 1 over r here. And how our switch works is that it's similar to the case of relay circuits, but instead of having a primary circuit, we are going to have a ring that's charged by, let's say, 1 μ-coulomb. And when we press the button, the object that passes through the circular ring will transform the circular hole into an ellipse, so that the curvature at the 2 tips of the ellipse increase, and therefore increase the charge density at the 2 tips of the ellipse, and therefore will trigger the charge sensor at the machine to let the machine work. And here's the calculation of the machine that we are going to design, and these are the charge density equation. And we assume that the electric potential is equal potential by the Gauss law, and then applying also the curvature at the 2 tips, we find that by putting back into the equation, we find that if the case is when the charge density is 10 times larger than the original one, then it will trigger the machine so that the essentiality of the ellipse will be 0.966, and the semi-major axis of the ellipse is 1.564, and the button design is here. And to actually make it better, we think that making the 10 times charge density will make the ellipse transform not realistic. And therefore, we make it as 5 times to make it rather make sense. And here's the result. And our second application is the secure water slide. And we firstly assume that the shape of a human body, upper human body is cubic, and the thickness of body or head is 1/3 to our shoulder length. And then put it back into the ellipse equation, we can find out a relation of the minimum perimeter and the h, which is the length of our shoulder. And to be more generalized, we then assume that ratio is not 3 and is k, where k is larger than 1. And for the case that when k is larger than or equal to 2, which most children can pass through the hole, then the smallest radius of the circular ring will be 0.964 h. And how this secure water slide going to work is that when the children is going to go down the water slide with their head out first, they will immediately feel some obstacle as the shoulder length is larger than the circular ring. However, if they go down with their lower part body, they will feel more lateral, and then they can squeeze through the circular hole and transform the circular hole into an ellipse. And the advantage of having this membrane at the entrance of the secure water slide is that it can make sure that it can give awareness for the children to have a correct posture before they go down the water slide, and also buy time for the safeguards to realize that the children is going with the wrong posture. And our third application is catching fish. We think of this based on this box, which this box consists of 2 membranes that's similar to the case of water slides. And the first membrane has a larger circular hole so that the fish can pass through it and squeeze through the larger hole. And for the small fish that we don't want to capture, can go through the smaller circular hole at the other side so that we can capture the size of the fish that we want. And the advantage of having this catching fish is that we can choose specific size of the fish and decrease the chance of hurting the fish, as the fish just have to squeeze through the circular hole and to transform the circular hole into an ellipse instead of hurting the fish. And also it will be more convenient for catching the fish, as the fish latch is time consuming. And to conclude, our project is based on the fixed perimeter and to make lots of interesting calculation. However, we face some difficulty when we try to divide the maximum area in terms of P, as the elliptic integral doesn't have a algebraic expression. But luckily, with using numerical method, we can find some interesting property, and we lastly can define an equation between the maximum area and the perimeter. And as this is the reference of our project. Thank you.